So hello everyone, welcome to Course Seeded. So today we are going to study the mystery of E and product rule of derivatives. So in last lecture, if you are not there, you must have already seen that I taught you why E is always decreasing with its increasing coefficient. So basically after 2, it just stops increasing much. So let's prove that why that happens. So obviously you now know what our E was. So basically let me tell you one thing, that an is a sequence, not a series, not an equation. So an basically is your number which you take when you are just solving this and tending to infinity for an. This is given that n belongs to natural numbers, which is under your real numbers, or you can say this is how n is defined. So suppose if you want to prove that for -1, -2, then obviously you don't have to prove that because this is by definition n belongs to a natural number. So obviously when you have, obviously the need was basically need was in the banking sector, and there you have to take natural numbers only. So let's go with this. You have to remember this, that n is your natural number, which is again which comes under your real number. So let's begin with the proof. So we have this limit. So basically let me write the n. N is basically your 1 plus 1 by n to the power n. So this is your n. So next you have your limit. So you can just write this limit 1 plus 1 by n to the power n tending to infinity. So since you know this is a natural number, we can just use our binomial theorem. So we can just expand this 1 plus, so basically 1 to the power n, which is again your 1, plus your n1, nc1 you can say. So next you have your binomial coefficient, which was n1, and you can say you have this n to the power 1 by n to the power 1 times 1 to the power n minus 1. So basically we won't be writing this 1 to the power n minus 1 because you already now know the sequence. Every power of 1 will just be 1. So after multiplying anything by 1, you will just get the same thing. So let me write everything over here. Then we'll have 1 by, let me write that as well, n, and we'll have here, should have this. Then we have your 1 by n to the power n. So basically this number goes over here, n minus that, in power of 1, and for this 1 by n, it goes as the same number. 1 by n to the power 0 is equal to 1. So I mean, you just know the binomial coefficient, right? Or the binomial expansion, how that works. So this is your final thing that you'll get. So let me write it in a cleaner way. So you have this n1, then you have your 1 by n plus n2, 1 by, you have 1 by n square. Then you'll have everything. Then you'll have your 1 by n to the power n. By the way, ncn is basically your e equals 1. So if you don't know what this is, suppose this is written like this, then you have your n factorial by n minus k factorial times k factorial. So what is factorial? You must know that. I mean, I've already taught that. Basically, you multiply everything from 1 to n for this to be an n factorial. So you have this. Next, you can have your this. You can just find what everything gives you. So basically, nc1 is your n factorial divided by n minus 1 factorial times n factorial. Sorry, not n factorial, times 1 factorial. So you'll just get this as n, which will be your n times 1 by n, which is again your 1. So we'll get 1 plus 1 plus. So this n2 and 1 by n square is basically your, you can write this as n times n minus 1 divided by 2 times 1 by n square. So if you just see it carefully, you'll just have this n square minus n by 2. You can write this as n square minus n by 2 times 1 by n square. Then what you can, or you can just do this. Let's say you have got this and this. So suppose for a general term, you know what general term is, right, in an expansion. So it's basically you take a number in between, which is, let's say, it is k. So k can be anything. It can be 1 to n anything. Then you write this as the general term and a bar k. So let's do this. We'll get n minus 1 up till n minus k plus 1 divided by your k, I think. Sorry, what was over here? Yes, so it was k factorial, not k. Basically, you will be left with this. So you're just getting k factorial. And this minus 1 factorial just leaves you with a single number. And this k factorial leaves you with k numbers over here. And you'll also have this 1 by n to the power k. So you can write this over here. Basically, if you are not getting it, then you can try solving it yourself. You don't have to rely on me completely. Basically, solve it yourself. I would recommend that, so that you can understand it in a better way. So you can just, these are k terms up over here, and you have your n times n up to k times. So you can just distribute each n in every bracket. So what you'll have, n by n times n minus 1 by n. Then you'll have your everything, and then you'll have n minus k plus 1 by n. So let's say you have this, then you are left with k factorial below over here. And if you see it carefully, you'll be left with 1, and then you'll be left with 1 minus 1 by n. Then you will be left with 1 minus, let's say this was n minus 2 by n. So this will be n minus 2 n. And so on. You'll be left with 1 minus, basically n by n is your 1, minus k plus 1, sorry, minus k minus 1 by n. Basically, you can just take everything in a single thing, basically outside the bracket, and you can just leave it as that. So, I mean, you can solve it yourself if you are having any problem understanding my equation. And then you're left with this. So then you'll have k factorial. So since we know this was supposed to be under this limit n tending to infinity, now you're already able to see what you'll get, right? So this was a single coefficient. So every coefficient will look like this. So you can just write, so you know that k equals from 1 to n, or you can say k belongs to, let's say, a set x, which is basically your 1 to n, 1 to n, where your x belongs to natural numbers. So you can write your k like this. If you don't get this, then in a simple language, you are getting 1, 2, 3, 4 up till n. So you have this. Next, you can just have your. This was supposed to be a normal data science course, but for some reason we are just going deep in the backend of your data science libraries, or ML libraries, you can say. So from ML libraries, we'll be constructing deep learning libraries as well. So just bear with me for a few more lectures, not just few more, but many more lectures. And afterwards, we'll be able to grab some great stuff. So we are left with this. So basically limit, let's say n tending to infinity for this specific coefficient. For this specific coefficient, you can just say that n is just tending to 1 by n, and 2 by n is tending to your 0, because 1 by n, limit n tending to infinity 1 by n is actually your 0. So you can just completely write this as 1 by k factorial. And obviously for all the coefficients, you'll write it like this: sigma of k equals 1 to n. And obviously you can remove the limit, because we just clearly saw that n just tends 1 by n, and all these numbers just tends to 0, or you can say they become 0 when n is tending to infinity. So this is what you get for your limit of a to the power n tending to infinity, where a to the power n equals 1 plus 1 by n to the power n. So you finally got this, your exponential equation. So what you can write, so this was basically your E, if you remember that. We defined this, or we gave this a name which was E. So this is a named irrational number. So named irrational number E has your value limit n tending to infinity a to the power n, which is basically your 1 plus, sorry, limit n tending to infinity 1 plus 1 by n to the power n. Where obviously you know that, your n is, so basically your n over here is natural number. Let's say you want to take it as a 0. Actually, n does not belong to natural number, it belongs to whole number, I think, because when we are doing this in the binomial coefficient, we are taking n as 0 as well. So yes, okay, so yes, we just can't say that this is just just for natural numbers. So basically n belongs to whole number, let's say, or you can say n plus this 0 over here. Well, yes, let's write it as natural only, because at some places you consider natural numbers as whole numbers, so it's not much of a problem. So let's say for this, or let's keep it like this only. People who understand, they will be able to understand this. So final you will have this. This will be your final equation, 1 plus 1 plus your 1 by 2 factorial. You can write this as 1 by 1 factorial as well, and 1 by 0 factorial over here. But you don't need to write this because of obvious reasons. 3 factorial plus 1 by 4 factorial plus your 1 by 5 factorial. I mean, let's not complicate things. Let's just write dot, dot, and dot. So this is your final E which you get. So just remember this, write this in your some short note, whichever or wherever you have created your short notes. Write this E equals 1 plus 1. This is the expansion of E. You should write it somewhere. From here we will be like finding the we'll also find the expansion of log as well. But let's try to prove our product rule. So with product rule we can just prove many more things. Basically after product rule you can easily prove your quotient rule. So that will be your question. That will be your homework. So after proving the product rule, you just have to prove your normal things, which was your quotient function or rule. So before we go to the product rule derivation, let's talk about few things about this E. So basically E wasn't just your any natural number or whole number. It was an irrational number which you got by chance because we had some necessity for this. So after this, which we know that, so after this we can also ask why this is less than 3. So let's prove that as well. So suppose this was 1 by 2 plus 1 by 4 plus 1 by 8 plus so on. So you know obviously that in a square of size 1, if you go by the half and then you half it again and then you keep going and you keep doing half and half, so you end with these numbers which will ultimately give you the complete area, which will be your basically 1. But since you know that this 1 by 2 factorial equals 1 by 2 and then 1 by 3 factorial is not equal to your basically it's equal to your one third of one third of half. So it's not half of half, it's basically smaller than that. And similarly, you get a 1 by 4 factorial, which is even smaller than half of half. So basically you get smaller than that 1 by 8 as well. So we are not just halving every number, we are just reducing it even more. So that gives you less than 1 thing for this 1 by 2 factorial plus 1 by 3 factorial and all. So 1 plus this number is less than 3. So you can just remember that E is less than 3, or by calculation you can just find that E equals 2 point something something. So let's say 7, 8 or whatever you want. So that's what we do. So next we can just have our next proof, which is basically we derive something from our general exponential equation. So basically this was for E. So we just proved that d by dx is basically our d by d e to the power x equals to we didn't prove this. We have to prove this now. So well, for this we will have to prove our product rule as well, or not for this, but yes, earlier for something I took like a product rule and I said that I'll be proving that later. So that's the reason I'm proving it over here. And you'll also know why product rule proof is very important for our data science course, because that will help you build a library which is actually like works for your proof. It doesn't just go like, yes, this happens or that happens. So proofs are very important if you are studying about data science. It basically builds your thinking, and obviously it just doesn't build your thinking, it builds your libraries as well. So raw libraries are basically built like that. So let's go with this. By the way, you can contribute to those libraries after you have studied this. So I'll be telling that later after this course is completed. So let's go with this, d by dx e to the power x equals to x. So basically for this we can just prove that d by dx e to the power x equals something, and for this a equals e, it comes out to be a to the power x. So let's try to prove for the general exponential equation. So obviously you know how to prove this, right? So first we'll take fx equals a to the power x. Then we know how we change this. Basically we do limit x tending to 0. H tending to 0. And then we just add a to the power x plus h minus ax divided by h is basically your dax by dx. So this I've already taught, I think in first or second lecture, third, fourth. I think in calculus lecture first I've taught about this. So basically the lecture 1 of calculus. So we have this x plus h minus a to the power x by h. So instead of h, let's write delta x, because h was basically your thing that we used to write for, or let's leave it at h only. Well, basically for the minute changes we can write delta x as well, but let's not worry about that for now. So we have this, and obviously you know what, you can write this a to the power x plus h is basically equals to your a to the power x times a to the power h. So you can just directly do a to the power x a to the power h minus 1 divided by h, limit h tending to 0. So by the way, we know that this is a continuous function, so you have to, like, you can just take these things out, that you can just say that this limit, what do we say, this a to the power x divided by, not divided by, h tending to 0 a to the power x by h x h tending to 0 times limit of your h tending to 0 e to the power h minus 1 minus 1. So let's take h over here because that will be more beneficial for us. So you have this. So you got a equation, basically not anything that's it does not have any h in its like base form, and we got it outside that limit. So for this you can obviously write this directly as e to the power x. So you can directly write this like this, and then you can have your limit h tending to 0. Obviously, because this was a continuous function, no, actually this doesn't have to be a continuous function, but it does. I mean, it's not relevant to h, so we can just directly write that this is a constant for this function. Sorry, this limit. Basically, it's not a constant, but it's a variable constant with respect to h. So we can just directly remove that from limit. So you have this, then you have your e to the power h minus 1 by h. So after this, you can just write that this is your limit LA equals limit of h tending to 0 e to the power h minus 1 by h. So we need some value now for which this becomes your 1. So basically what I want to say is, so for d by dx to be equals to e to the power x, we need for d by dx equal to, we need this limit, or let's just actually write LA over here. We need LA to be that basically it has to be like something equal to 1, right? So basically what does this mean? So basically we need something that is that it depends only on the base a, and also it is independent of x. It is independent of x. Basically, if it is independent of x, it directly becomes independent of h as well. As you can just see that depending it on x, make it like x plus h gives some other value and x minus h gives some different value. But if it is independent of x, then h doesn't matter. It can be as large as possible or as small as possible. So we have to make it independent of x, right? So can you like imagine anything that makes it something like that? So let's make this your question, because for now we have not yet studied about this integration. Otherwise you can just directly find that it will be directly, we can directly find that it will be equals to some constant, which we can just find that it was e. So for that we'll be just we won't be doing this directly right now. So we are left with this LA equals 1. So the things that we need to do, or the things that we need to solve, the things that we need to prove or solve. First thing, this is LA equals 1. This LA equals 1. Basically it is independent of x and it depends only on the base a, and that a will be your e, obviously. So let's say, let me directly write this LA equals 1, or you can say to solve LA equals to 1 for a equals c. So we are left with this, and second we are left with our I think that product rule. Next we are left with our quotient rule. I don't think there is anything else that we are left with. So after doing this product and quotient rule, we'll be going to the chain rule as well. Then we'll be going to mean value theorem, and then we'll be going to Taylor's theorem as well. That will be our completion of phase 1 calculus. Then we have 2 more phases, which is our phase 2 and phase 3. So yes, it's a long journey. So let's begin with our product rule proof. So at first you have, let's suppose you have this hx equals fx times gx. Let's say you have this hx equals to your fx times gx. Next, what you can have your h dash x. Okay, so let's say you have this. Let's say you have your h dash x equals to your. Also, I thought I'll be telling you about what uses are there for these proofs to be in AI. But let's keep it for those days when we are going to directly implement them. So instead of telling it again and again, I'll be just directly implementing that at a single day. So instead of wasting time, we'll be just directly using it. So you have this hx equals fx times gx. Okay, so I'm glitching heavily. Then you have this h dash x, which is your derivative of hx equals to something which we don't know yet. So let's begin with our proof. So let's say you have this h dash x equals to your limit of x tending to 0. Basically, you'll be just delta x tending to 0. We'll be just adding delta x to every function. You can use this h as well, but for this proof, I would prefer using delta x instead of h, because that's how I remember it. Well, obviously, I don't remember everything. We'll have to prove that along with this. So you have this gx plus delta x. Okay, so this has to be something large. So let's say minus of fx times gx. Okay, so let me just rewrite that. So we'll be taking some small characters. Fx plus delta x. Obviously, you have to remember that this will be your limit delta x tending to 0. Then you have this gx plus delta x minus of fx times gx divided by your x plus delta x minus x. So you can basically have your things over here. So let's not worry about limit right now. Let's say we have this fx is this function. So this is basically your ab minus cd. Let's take small. Okay, so we have this ab minus cd. So obviously we don't have any algebraic identity for this. So what you'll do, you can just say that we have fx plus delta x, fx plus delta x, and we'll take a different this gx. We are basically combining these two so that we can just rearrange them in a way such that we can just factorize them and get this outside the limit. So we have this fx plus delta x times this gx, and then you have your minus fx plus delta x times gx. So we are basically going to implement this plus and minus, which is basically equals to 0 only. So we are just adding 0 in the numerator. So let's add that. So after adding that, let me write it as f. So let's say x plus delta x equals to your capital X. So I'll be writing f capital X g capital X plus f capital X. Sorry, let's take the minus one over here. Gx. This is basically your small x, and this is your x plus delta x. X plus delta x. So this is your gx. Then you have your f x. Then you also have your gx. And let's say we have okay, so this was supposed to be plus, because this we took as minus, so we have to take this as plus. Then you have your minus of fx dot gx. So this can be written as this: f capital X g capital X minus gx, and obviously you have your plus plus your this fx gx times your this f capital X minus small x. So this is what you have. Then you can say this means this implies that our f x plus delta x gx, sorry, let me write it as capital X only because it won't fit over here. So we have this gx minus gx. Then we have this delta x over here. Let's say we wrote everything, and then we have this delta x, and then we have our limit delta x tending to 0. So what you can do, you can just say that that you have to just write it in such a way that everything gets a sequence, basically where you have to eliminate whatever is there inside, whatever is not needed inside, we can just take that outside. So basically what I mean is, let's say you have this this f x plus delta x times gx gx plus delta x minus of gx. So this is basically your first one, and you have this second term, which is your gx times your fx plus delta x minus fx. So basically you have these two these things, functions. So let's say we can just directly write them as this, then by delta x, then we can just have this, and then we can just write limit h tending to 0. Sorry, delta x tending to 0, because we don't have any x, h. So you can basically write, you can just take this outside. So I'll be directly doing it over here instead of taking it again and again outside. So you can just leave it outside and write delta x inside for both the equations. Basically this was a plus sign, so we can just do that. So now you can see this x plus h minus x divided by h. Does this look like does this look familiar? So if you have guessed, obviously if you have guessed derivative of gx and fx, then you are well and good. So basically this is the derivative of gx written over here, and this is the derivative of hx written over here. But additional to that, we also have this fx plus delta x and this gx. So basically we have two more functions in product. Basically for this plus, you can just directly do this limit. Obviously we know that this whole function is continuous. So let's not let's talk about it over here only. So you have to notice that fx and gx have to be continuous. Basically if they are continuous, that means basically if they are differentiable, that means that their continuity exists. So basically they are continuous. So the derivative has to exist for this to like possibly take place. So they are continuous. So what you can do, you can just write you can write it over here that limit delta x tending to 0, and then you have this a. Basically this complete is your a. Then you have plus limit x delta x tending to 0, and then you have your b over here. So let's say we have this is equals to your limit x tending to 0, delta x tending to 0. So let's solve for this first a1. Let's say we have this f delta x minus fx, sorry, not minus fx, We had gx plus delta x minus gx divided by your delta x. So obviously you can directly see that this will be equal to fx. Basically, let's prove that as well. So let's prove this, that it will be equals to f dash x, or sorry, not f dash x, fx plus this, sorry, times this g dash x. So basically limit of f x plus delta x is fx, everyone knows that, but let's prove that as well. So for a continuous function, you just know that we can just directly insert delta x to be this, but let's say that fx was equals to this x by x, or let's say it was equal to your let's say it was equal to something like a to the power x divided by x, or we can go with 0 to the power x by x. Yes, this looks even better. So for this, let's try to find its what do you say, limit or derivative, or instead of keeping it as 0, let's keep it a only, or we can just write it as, okay, so let's leave it over here. So we have this delta x tending to 0. This looks good to me, so I just left it over there. Let's make it 0 again. So we have this delta x tending to 0, then we have our fx plus delta x divided by your this basically divided by nothing, because that division will go over here, so we don't have to worry about that. So you have this. So let's say x plus delta x, basically 0. Okay, so I actually took this wrong. So let's say this was supposed to be x to the power x, or 0 to the power x. Okay, so actually I'm not able to get any function in my brain currently which just fails on this. So let me just think carefully what function will fail actually. Let's say we have this fx plus delta x, then we have our some function, let's say this was x, basic x, and it'll just yield this. But let's say if we had something like this, then it will yield plus delta x. But if it was supposed to be like this, x to the power x, or let's say we have x to the power 0 plus x. Oh god. Let's say we have this. Okay, so I exactly don't. Okay, so let's take some function which is, I think, 2 to the power x. So for this we had, or let's take this x plus x minus 2 whole square. Then I think x was tending to 2, right? So let's say x equals 2, and we also have our delta x tending to 0, which is basically your h. Okay, so I got the function. So let's say fx is your x minus 2 whole square. Let's say we have this. Let's say we have this instead. This would be even better. X square. So we have this. We can just convert this to like x minus 2 by x. So we just basically need a division by 0 over here, which will basically yield some false values. So basically for this function, as you can see, it will break. So basically this will be a discontinuous function, and this cannot be like derived basically directly that. So we just know that for a continuous function, basically suppose this is the function, and over here this is called the continuous function. So x plus delta x, which is basically your this place, will actually yield something similar to your fx. So you can just directly say for a continuous function delta x tending to 0, fx plus delta x. So basically there was no like rocket science over here. We just know that this is a continuous function, and this all just happens that for a continuous function, it will be similar if the limit x is tending to 0. Basically, it will just meet at the same point. So we can just write it as fx directly. No rocket science over here. But I was trying to like tell you why it can fail at discontinuous functions. So basically, let's see that using graph only. Let's say if this was the function at x plus delta x, and this was a function at x. So you can see that there is a lot of difference over here. Basically, this is called the discontinuous function, where you don't get a straight line. Instead, you get it in the points. It is basically a discrete function. For now, you can just remember that discrete functions are your functions where your derivatives fail. So we have all this. So let's go to this proof. So now we know that this limit x tending to 0, sorry, delta x tending to 0, fx plus delta x times limit your basically both are continuous function and both have your seniority. Basically they don't are like they are not like dependent on each other, so they won't just have any problem in getting separated. So that's the reason I'm just separating them. So you can write this. So you finally just can directly see, since we proved this, so you can just say fx times g dash x. And for obviously the second one, you can just prove that as well, gx times f dash x. So you finally have for a function for hx equals to your fx times gx, h dash x equals to your basically derivative of hx equals to your f dash x times gx plus g dash x times fx. So you have all this. Basically, you have all this over here. So I think this should be it for today. So next time we are just going to like solve for quotient function and quotient rule, and there was one more rule. I think it's chain rule. Yes. So we are going to solve for chain rule and quotient rule, and after that we'll be just solving few questions, basically math questions. Then we'll be going for data science code. So I think that's it for today. So your question, you already know that you have to your homework question is prove quotient rule. Prove quotient rule with what we have studied till now. With what we have studied till now. Basically, don't use your integration and all. So you have this. So you have to prove it according to what you have studied till now. If you haven't made notes, from the next lecture, we'll be providing notes as well. So you don't have to worry about the notes or anything. So thank you everyone. Thank you for watching. Let's meet in the next lecture. So yes, thank you.